Okay, so let's quickly review what we went over last lecture about basic quantum theory. The most important part is the basic quantum system. We consider a particle in discrete position on a line, and then we consider single particle spin system. And this line can be called x0. Let me call x0, x1, x2, xn1, n minus 1. So this is the classical quantum computing system. And then for each state, if it's x0, we write in this so-called cat notation, and then with 1 in that state 0, the rest are 0. And with x1, we say the x1 position is 1. And we can write this in the superposition notation for each state, but for more clarity, we can also write just using another symbol, say cat psi, not to be the entire, is basically the same thing as the complex number plus each state. And those each complex number is called a complex amplitude. I'm going to start my video. So, okay, and in contrast to the real system where the probability is actually correspond to the real number in classical computing, in quantum computing, the probability is correspond to the modulus, square modulus of that complex number. So that's some of the very important concepts in the classical quantum computing system. By the way, this is a so-called basic classical quantum computing system. If instead of consider each quantum state a single dot, x0, x1, if we consider that the wave, that basically becomes a string theory, and that's will be more minus thing, just more generalizable to describe this quantum system. Okay, that's a bit off the top. My understanding, that's the classical system. You have each particle as a dot, x0, x0. In the quantum system, we consider the whole thing as a string. In a string set. Sorry, my office door is not closed. Okay, my apologies. I forgot to close my office door before the class started. Okay, so one very important concept is called transition amplitude, which basically describe a start state and end state, how the quantum state transit from the start to the end. When this is actually quite relevant to the observable state. So we often write this as the bracket, which is inner product of the two, the start state and end state, and that will be the conjugate, the inner product of the two complex vector. The first one will be the conjugate, and then followed by the other one. Okay, so that's what we covered last time, and this time we are going to focus on the observable. Those are my understanding. Those are just some very smart people has already proved or figure out. The physical state is actually physical observable is actually described by the Hermitian operator, let's say omega. And then the eigenvalue in that omega are the only possible observables, and the eigenvector of that omega basically form the basis of that state space. There must be books and books to explain this. So the Hermitian operator basically means the matrix equal to the Hermitian transformation of Hermitian operation on the matrix itself. So given this, another another important concept maybe is the moment. This is actually a bit tricky for the classical system, but so even though each particle is a dot on a line, you actually, and the system is discrete. For apparently, we can still say delta x on that line. This is actually quite interesting. You wouldn't do that in discrete math this way. I'm pretty sure if we do this in discrete math, it'll be problematic. So anyhow, but this in quantum system, this is the definition. So even though each particle is a dot in the classical system, we can still consider the difference between the state by delta x as the moment. I guess in the quantum world, many things are different from what we often learn in the classical physics, classical math, or something. That's the observable we went over last time. I think I also had the. I thought I also went to my example code last time. Yes, I did. Yeah. Oh, it looked like Dan also started with GitHub repo on this. Very good. Thank you. Yeah. So those are the two very basic concepts, quite abstractive, but for our purpose, we are more interested in how to apply this in quantum computing, how to use that in applied quantum computing, either in engineering, material science, or chemistry, or any other things. We are not really interested in how quantum computing will work as a theoretical physics perspective. We are more interested in just how to apply it. So let's see my code. Oh, there's actually another observable is actually quite related to the quantum computing later on. Let me write it down here. It's another part. Is called the spin operators. Spin operators. Since the particle had a polarity of spin, so we can actually using the observable operator to see is the spin in the direction in x, y, or z direction. So the spin operator sometimes in the book is actually written as the spin operator z direction will be the h bar 2. So those are the x, the spin operator, the book. So we actually can verify those should be the Hermitian matrix. So the book actually, I think I have the Python code to verify it, do I? Let me look at my Python code. Not exactly the same thing, but it's similar to this. Yeah. So in the books, let's see. In the book, it shows that if we observe the system twice, oh, I see. So it actually first. Sorry, I confused a bit on my own notes. So the book actually first go over the property of the Hermitian operator. So the sum of the two Hermitian operator is also Hermitian. And I think that's where my Python code is. Yes, so my Python code shows the sum of the two Hermitian matrix is the Hermitian. And then my Python code showed the example 4.2. Oh, sorry, I didn't share my screen, did I? No. Yeah. So so my code first show the sum of two Hermitian metric is Hermitian. So first, A and B is Hermitian metric. Hermitian metric means the diagonal must be a real number. Yes, that is, yeah. So conjugated transpose of A and A are equal numerically all close. So they are close, A and B, and then we added A and B together, and C is still Hermitian. Yeah, so that's one example. 4.5 book example 4.5. That's actually jumped over the spin operator. Okay, so I didn't have a example on the spin operator. Okay, I apologize. I missed that exercise. So the next the book actually, let me see. We actually missed the I actually missed the commutator example. I might have to add on next time. I come up with a commutator example. The book the two spin x s y and x0 spin operator. So okay, let's see. So Sx. Oh, sorry. Let's just use A as the 0, 1, 1. Oh, this is Sx. Okay, so this is Sx. Sy minus I. That's correct. Sz 1. Oh, actually, Sz is wrong. Sz is minus 1. Oh, that's Ss. Sorry, this is this part I didn't prepare well. So I'm doing this on the fly. This is Sx, not Sz. So that is correct. So we put the Sx plus Sy. And let's just still call that AB. That might make it a bit easier. Okay, that'll make it a bit easier. Okay. Okay, let's see. So this is the commutator of Sx spin Sx and spin operator Y. If we apply the commutator of SSXY, what I got is A is what? A is Sx. That's correct.
Yeah, they just factored out the constant 2i.
Okay, that's correct. Let me see.
Yeah, yeah.
That's
yeah. They just factored out 2i, so their matrix looks different. The book matrix looks different, but I think it's the same matrix because they factored out 2i as a constant.
Very good. Yeah, I agree. I have to. Yeah, it is. That's right. Okay. Oh, that would be a lot of change. Okay, I'll just leave it there. So, commutator example for Sx. 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + Okay, very good. So this is the equation 4.54. Okay. All right. Okay. Oh, I did this. We got. Yeah. So you can try SY, spin Y, spin Z, which is two more equation on your own. So. Okay. Yeah. So this is the commutator, and based on this, we actually can calculate the expected value at the variance of the states. This is actually will likely be very important in the applied quantum computing to solve some problems. I can see you if you think about the expected value and variance is also two important concepts in many basic statistic or measurement. Okay, so let me go back to my iPad to see whether expected value and variance. That's right. And I think I also had a Python code to show that. Yes, I did. Okay, but let's first go over the basic definition first. So the expected value is turned as, let me write it down. Of apply omega on a state is turned as that's the expected value. And the variance once we have the expected the variance, the definition is at operator minus the mean followed by the indicator. So that's the in the classical way, that's very often we say that's the mu, and this will be the x, and the variance will be x minus mean divided by the standard deviation. But in a quantum way, the concept is there, but the operator are a bit different. So. Oh, sorry. The variance actually the square of this is my apology. Without it, the variance is actually the square of that. Not really square, inner product of that. It's similar to the standard variance of square, but in quantum way, this is actually the inner product. So. Yeah, apparently people who study quantum computing must have very good handwriting. The the little parentheses, different shape really mean different things. So, and then that's the inner product. That will be the angular bracket. Smooth one is just to show the number of it to the symbol of the self. And with respect to that side. So, my understanding, this will be very similar to the classical computing method, classical probability method, variance. That part, yeah. So it's in a quantum way, this is become the inner product. That's just my way to trying to understand this. So, and then this is a definition. The book have, and then there will be followed by a few examples. That will be example 2, 4. I'm going to write down and then show the Python code to calculate that. So this is book example 4 to 6. So in this case, we have omega, which is this is actually a theoretical example. That's fine. Lambda 1, lambda 2, 0, 0. And then we have the book actually can show the entire formula of this. Let's find an example we can use for the Python. I'm trying to see which example my Python could use. I say example 4.2.5. I have to search for this in the book example. Oh, I see. I found it. Okay. Example not 4.6, 2.5. Let's use 2.5. My mistake. So in this case, psi is and omega is okay. So that's 4.2. And the mean is calculated as 2.5. Okay, the book actually So the omega there to omega there 2.2. Yes. So let me see. So omega on phi will be 1i minus I to this is for expected value. Expected observable, sorry. Minus 2. Plus 1 plus 1 for 2, is that correct? Yes. And then the next one is the okay, so that's the, and then the expectation. Expectation will be, which is omega phi and omega psi and psi itself in the product, which will be first is the bra of that. So that's this and this. So that will be two minus 3, there are 2. And then followed by the phi, which is, oops, psi, sorry. This is the bra of the upper part. Oh, I just, okay, I'm going to continue to write. I just realized I overlaid my writing. Sorry, can I undo this? Oh yeah, I can undo this. Okay, yeah, so this is the bra of that. Okay. Which is 2 divided by 2. minus 3 divided by 2 I squared. So that's plus 1. 2 is gone, 2 is gone. Plus 1, plus 1. So it's 5 plus 2, 2.5. Okay. Oh. Gee, hand calculation is hard. So let's see our Python code. Example 4.2 in the book on expected observable. Okay, so that's the psi square 2 square 2 over 2 I. Okay, that's a psi. This is omega. Is that correct? Let me reformat this. Omega is 1 minus I 2. Okay, that is omega. And then the first omega psi is the dot product, and then follow the omega psi and the vector dot point. So that is 2.5. The observable is 1.2. That's correct. It's 1.4. I guess that must be 3 over 2 square 2 I. So, okay, so 2.5. The result, final result is correct. Minus 2 minus 2, is that correct? Yes, that seems to be correct. That's just another example, I guess, yeah. So, okay, so next part is, I think it's a similar thing, but now we calculate the variance of it. So that to be, that's the side, it's, that should be the book example 4.427. That should be, I think that's built on 4.425. Let me double check. Example 427. Yes, yeah. Basically, using the same psi and omega. Now we are calculated the variance. So that's the same psi. Omega is the same. And that's the observable vector, expected value. And what's the definition of variance again? The formula of the, let me look at the formula, the variance. Okay. Inner product omega minus expected value with the indicator function. So this is the omega do that omega squared psi. Expected value squared. This is actually using the expected value minus expected value square is basically the same thing. So this is so and we got it from the book example 4 point, which is that 0.25, is that correct? Let me see. Where is that example? That's correct. Let me see. Yeah, so this is basically use the same formula. So variance x equals expectation of the x squared expectation of x. Apparently this still works in the quantum state. So that's the expected value square itself, and then the squared observation, and then expected value. Omega squared observed squared. Yeah. So we got a 0.25. So that's just a different version of it. It's still okay. So those are fortunately in Python Qiskit, those will be all taken care of most of the time, and we don't have to do the manual calculation all the on our own most of the time. So okay, And the next part of the book actually talk about measuring and dynamic. Those are actually most relevant to the quantum computing part, but the book actually really didn't go too detail about it. And presumably because we leave that to actually the quantum computing exercise. So there is actually indeed another topic we have to mention is the quantum entanglement for the multiple system. Let me. So that's it's probably easier to explain that using the actual IBM Qskit to show that. Yeah, the old code doesn't run in the code lab anymore, so I'm going to just go directly to the hello world example. So, yeah, unfortunately the previous code all doesn't run in Colab. So, but for the IBM, let me put that in the chat. Oh, somebody say quantum handwriting. Okay, good one. Okay, so excuse me.
Yeah, that's when you were discussing, the little finite differences in the notation.
Oh, is it? Okay. Sorry,
Yeah.
I didn't notice at the right time. Okay, but it's a good one. Sorry. So this is IBM. This is not a run. I haven't tried this code to run it. I did try it in the composer state, but this is that for today. We just trying to explain the entanglement. So this is hello world example of the Qskit and quantum computing using the IBM system. Just 1 year ago, we can still run this in Colab. But right now, let's just read the document and try to run in IBM system instead of Colab. So in this case, we are going to use the quantum circuit. So this is a bit ahead of ourselves because in the book, chapter 5 started to talking about the quantum computer architecture, bits and qubits. So this is a bit ahead of ourselves, but the point is trying to explain the quantum entanglement. So we have two qubit here, 0 and 1, and we first apply Hammer gate, which is give a superposition. And then we applied so-called controlled gate using the 0 as a control on the Q1 state. And then we followed by that two, look like when you read the instrument, if you read the old temperature, humidity, that's the meter, or gas meter or water meter. That's how the meter basically is a reading observation. So, and we read on the 0 gate and the 1 gate, and that's is basically measure 0011. C not controlled X gate, CX. And we can actually run this on the IBM computer, but we can also run this on a simulator. In Colab, we often just run that on simulator. I actually did send something before the class, send it to the IBM. I'm not sure, but I forgot which page I use it. But if we send it to the actual IBM quantum computer, we have to wait for it to execute it. So once, so in this case, we basically had the 50, because the two states are in the so-called entangled state, they are correlated. Let me see, run your code. Yeah, this example is actually indeed oh wait, this is actually simulator. This one use a simulator on this. And then we plot, this should give a uniform distribution between the two states, between the observable. Which means there are actually other possibility which is not there, which is the point is 0, 0 and 1, 1. But the other two states, because the two states are not entangled, they are not what's the word for it? They do not occur. Yeah. So in theory, with the 2 qubit, we may have 0, 0, 1, 1, 0, 1, 1. If they are not entangled, we should see uniform distribution all 4 possibilities. But in reality, well, not really in reality. In the entangled conditions, they actually only occur in the 2 possibilities. So that's the explanation, try to explain the entanglement. So basically now the 2 qubits are correlated, not separatable. So okay, this is really a lot. Okay, for one day.
How did you specify them as entangled? Was that what the H or the second line in your code was?
No, the entanglement really achieved by the H plus the C naught gate. The H is just superposition.
Oh, okay.
Yeah,
okay,
the entanglement rate achieved by the H gate and the controlled gate, controlled C naught. This H plus the C naught achieve the entanglement.
I see.
Good question. Yeah. So okay. The H gate itself is just superposition. Okay.
Thank you. Yeah.
This is really a lot. When I try to copy paste this code into Colab, it doesn't run. In fact, even the IBM circuit doesn't load anymore.
I tried this, doctor, was the lab. If you copy that code and paste it where you were now, just click on lab tab, the one that says lab here.
It runs?
I didn't open it that way, but I was able to open, like, select the Qiskit.
Okay.
You remember the first link that you sent it to us on the
yeah. Okay. Let me.
It worked actually.
Hold on. I organize my GitHub with some easier to use bookmark. So hopefully it's useful. IBM Lab.
Okay, yeah, that's nice. Yeah, here when you say file new, text on file on the top here on the right side.
You see, some of my code actually even 3 years ago are still there. So Even though they say they will purge it, apparently they did not.
The one that says Qiskit, doctor.
Yeah. So wait,
and then the last one, Qiskit notebook.
Oh, you just go directly to Qiskit notebook.
If you, I
Yeah,
didn't go file again, file new, and then the last one, Qiskit not yeah, this one. If you paste the code here,
not this one.
where's your code?
Yeah, this is going to run, you're saying.
Yeah, copy that and paste it there, it will work. Here in the last cell. Yeah.
Oh, it's automatically imported.
Yes.
I see. Okay, very good.
And then run that on the top. The run button. Yeah.
Ah, excellent. Yeah, it is. I mean, it's IBM, the own lab, certainly it runs here. So good, thank you. Yeah. So, and then let's, okay, now we can actually see the runtime result. Okay. Oh, sorry. I'm not sure why they don't give everything in one cell. It is waiting now. So
can you just copy the entire cell from the new notebook?
wait, there's the entire cell, and where is the new notebook?
When you made
download
your
the
Qiskit
entire
notebook.
I see.
Well,
Okay.
when you made your new Qiskit notebook, there was just the only difference is they had a bunch of imports at the top.
I see. Okay, thank you. I didn't notice that. Yeah, maybe you can just download the entire notebook, I guess. Yeah. So okay, good one. Maybe next time. Actually, I download.
So that one that I posted should enable you to run it on any local IPNB file notebook.
Nice.
Yeah.
It upload a notebook, download. I don't see upload. Where is upload? Oh, here? Is that here?
Maybe.
Yes. Okay. Hello world. Oh, there's already word. That's fine. Let's overwrite the old one. Where's my hello world?
It's down here, I think.
Yeah, second ago. Okay, very good. Oh, I see. Oh, it's already wrong. Okay. Let me rerun and clear the output. Is there a clear result? No. This is not a standard notebook.
No.
The standard notebook had a clear result part. This one doesn't have it. So okay, but it's good at least. But I already run this one, so yeah, I'm still waiting. See. Oh, this one indeed sent to the queue. But this is a simulator. Why the simulator is waiting so long? That's really a bit. I thought the simulator will be faster. I don't know why it is waiting here. Yeah, but it's good. At least the IBM thing is still consistent running. So I guess the homework is for all of you to
Are you? Hello?
Poster is very interesting. Apparently, we can drag and drop just to build a quantum circuit. But quantum lab we can run the notebook as we just showed. Yeah. So this is actually apparently one of the platforms used to connect with the real IBM quantum community. You can see I tried something a few years ago on the IBM, actually indeed some quantum computer there, get some result there. So, but in those cases, you have to submit a job and wait for it. Yeah. So, yeah. So as a homework, maybe you can we can now try to learn IBM quantum. It actually has its own tutorial, very nice. Yeah. So, although its own tutorial is more like towards the programming and IBM system, but it's still good. And it also has some basic quantum computing part. It's actually quite different from what has a different emphasis. It also emphasizes on probability and quantum computing. Classical operator, it has its own way trying to explain what's the difference between classical and quantum computing. Instead of using the double slit experiment, it's actually using a different analogy. I haven't go through this, but it will be worth investigating IBM system versus our textbook system. And this part is similar to what we just went through. This basically the basic concept of complex vector. And those are the operator. That will be the Hermitian. And they use dagger, but handwriting with dagger is really hard. So, yeah, and then it goes to the Python, and this part we also went through it. So, yeah, it is the